Dear colleagues, in this presentation we want to show you how to recover energy from a ventilation system by using different types of air handlers. As usual, we will display the basic theory first, and then we show some numerical examples to assess advantages and disadvantages of each solution. Let's see together. What is heat recovery? Heat recovery means reusing the inside air to preheat or pre-cool the fresh air in order to reduce the heat cold generation capacity, reduce the running cost, reduce the maintenance job, for instance, for filter cleaning. There are 5 possible ways. First, mixing air. Second, air-air plate exchanger. Third, air-air rotary exchanger. Fourth, air-water double exchanger in closed loop. And fifth, thermodynamic recovery. In the schematic, it is represented a typical air handler. The different components are displayed with red numbers. Starting from the left, air inlet damper, number 2, filter, number 3, heat recovery exchanger, number 4, heater, number 5, ventilator, and number 6, silencer. As you can see, there are 4 air streams shown by different colors. Outside air is in green, supply air in blue, extract air in yellow, and exhaust air in brown. This is the most general type of air handling unit, with 4 gates and bypass inside. If the bypass is closed, the extract air and exhaust air are the same, as well as outside air and supply air. Let's speak now about enthalpy. The enthalpy capital H of a humid airstream depends upon 2 parameters among dry bulb temperature, wet bulb temperature, absolute humidity, relative humidity. If dry bulb temperature capital T and absolute humidity X are known, then we can use formula number 1, where Cp and R are constant values hereby displayed. Cp is the specific heat value at constant pressure of the air, and R is the latent heat of the water. For any transformation, delta H can be taken from the Molière chart. If there is only sensible heat transfer from T1 to T2, then we can use formula 1a. If there is only latent heat transfer from X1 to X2, then we can use the formula 1b. Let's start from the first type of heat recovery, that is the mixed air. To allow it, we need a special type of air handler with only 3 gates. 2 gates for intake and 1 gate for supply air. The intake streams are the outside air and extract air, elsewhere called indoor air. In this case, the whole enthalpy of the indoor air can be recovered. On the other hand, there is risk of contamination. The enthalpy balance when 2 streams of humid air are mixed together can be written as per equation number 1, where the subscript IDA stays for indoor air and the ODA for outdoor air, while mix is the mixture. By solving the equation for the enthalpy of the mixed air, we find the expression in red. Assuming that the enthalpy of supply air is known, that actually depends upon the heat load of the system, the heat demand of the air handler is a product of the mass flow of the mixture and the difference between the enthalpy of supply air and the one of the mixture, as per formula number 2. The second way of heat recovery is by using a plate exchanger in between supply and exhaust air streams. The air handler
looks like in the picture. The outside air, after the filter, enters the exchanger where it is preheated or pre-cooled by means of the extract air. Then it goes into the coil and it is pushed to the ambient by the supply fan. The extract air is also pre-filtered, then enters into the exchanger and it is pushed away by the exhaust fan. The two air streams are physically separated, so no contamination can take place. In the reality, the exchanger has a small leakage, but this is marginal. The problem we need to solve is what is the temperature of supply air after the exchanger? With this info, we can estimate the heat demand of the coil. Known is the temperature of extract air T11, the temperature of the outdoor air T21, and the efficiency of the plate exchanger eta X. The efficiency is displayed as per Formula 1 above. The unknown temperature T22 we can get by solving the equation number 1. The heat demand of the coil is the product of the mass flow of the outside air and the difference between the enthalpy of supply air that is given and the enthalpy H22 corresponding to the temperature T22 already found. This enthalpy we can calculate if we assume same humidity X as the one of the outdoor air. The mass flow is the outside air stream since no mix is taking place.
The third heat recovery way is similar to the one seen before, but the heat exchanger inside the air handler is different. Here we adopt a rotary exchanger that is more compact and more efficient. The thermal wheel inside the air handling unit works as a thermal mass and transfers the heat among the two air streams, thanks to heat rotation. The air streams stay separated and do not cross each other, even though a certain leakage takes place due to the air trapped inside the honeycomb of the wheel. That is the reason why this type of exchanger can also transfer latent heat. To make it simple, we won't consider it in our presentation, however. Should we need to calculate the temperature of the supply air after the exchanger, we proceed in the same way as per the plate type. We neglect here the internal leakages that strongly depend upon the wheel type and location of the fans. Moreover, we consider only sensible heat transfer. The heat demand of the coil is given by a similar formula. Of course, we expect here a lower value since the exchanger has a higher efficiency. Another possibility of heat recovery using exchanger is to use a closed loop by water. Here, the air-air exchanger is replaced by two air-water exchangers. The advantage of this solution is that the inside air channels and the outside air channels can be distant each other. Moreover, there is no risk of contamination even though one of the coils has a leakage. On the other side, the equipment is more expensive and energetically less efficient because of double heat transfer steps. On top, we must consider the consumption of the circulation pump. Hereby a schematic with details and a picture. As you can see, this system is something more complex. There is a complete new hydraulic circuit in between the two air streams. The formulas for calculating the temperature T22 and the heat demand of the coil are the same already seen. Because of the lower efficiency, we will find a higher heat demand in this case. The last way of heat recovery is not using an exchanger, but the thermodynamic effect of increased EER or COP when using the inside air for either cooling the condenser or for heating the evaporator. In the coming slides, we will refer to the cooling application that is a chiller, but similar considerations are also valid for heating, let's say for a heat pump. In the schematic is displayed an air handling unit with integrated chiller. The inside air R is partly mixed with the outside air FA and partly exhaust to cool the condenser. In the picture is represented the diagram enthalpy pressure of a coolant and its thermodynamic cycle. There are 4 stages: 1-2 evaporation, 2-3 compression, 3-4 condensation, 4-1 expansion. Given are the evaporation and condensing temperature and the efficiency of the compressor. From the diagram, it is possible to find the corresponding enthalpy values: capital H1, H2, H3, and H4. Let's consider the case of a chiller. The corresponding EER is the ratio between the enthalpies at low pressure from 1 to 2 and the compression work that we can express as delta enthalpy from 2 to 3. Because of the heat recovery, the condensing temperature drops, thus increasing the EER. Definitely, the electric power WE needed to achieve the same cooling load W drops as per formula displayed. So far, we have seen all different methods for energy recovery just from a qualitative point of view. In the second part of the presentation, we want to show 5 examples, one for each recovery way, and quantify the benefit. For doing that, we refer to a common problem whose cooling requirements are hereby displayed. Inside and outside temperature and humidity are given, process exhaust air is known, as well as heat gain from surfaces and from machines, lighting and people. The heat gain due to ventilation we can easily calculate. That is a product of the exhaust air flow M0, its density ρ, and the enthalpy difference between outside and inside air. We find 110 kW and we call it Q2. Adding the remaining two loads, Q1 and Q3, we get an overall cooling demand of 290 kW. That is the minimum cooling load we need to provide. We will see the reason for this meaning afterwards. To balance the airflows, the fresh air intake, capital M0, must be equal to the exhaust. The recirculation flow, capital M1, we set to 34,000 cubic meter per hour. The airflow after the mixing chamber is the sum of capital M0 and capital M1. We get 48,000 cubic meter per hour. The enthalpy of the air streams are capital H1 47.8, capital H2 72.6 kJ per kilogram respectively. The enthalpy of the mix is then 54.8 kJ per kilogram. The supply enthalpy after the cooling coil must comply with those conditions: saturation, so humidity 100%, and absolute humidity equals inside the ambient. We assume there is no reheating after the cooling coil. From those conditions, we get the enthalpy of supply air, that is 36.5 kJ per kilogram. To check if the set value for M1 is correct, we remember we have set 34,000 cubic meter per hour. Let's calculate the sensible heat transfer. That is a product between the density ρ, capital M, and the difference between the enthalpy of supply air and the enthalpy of the air in the room. We get negative 185 kilowatt. That is very close to the sum of the quantities Q1 and Q3 that we have given. Also, the gas value is correct. The total cold input is then the product between the mass flow and the difference between the enthalpy of supply air and the enthalpy of the mixed air. We get negative 289 kilowatt, practically the same as the overall cold demand of the system, as we have seen in the previous slide. Here we have the psychrometric chart with the corresponding transformation steps. P1 represents the condition of the inside air, P2 the outside air, P mix the mixture, and P sup the supply air. The extract air through the air handler, capital M1, we set to 34,000 cubic meter per hour as done before. To balance the air flows, the fresh air intake, capital M2, must be equal to the sum of capital M0 and capital M1, also 48,000 cubic meter per hour. Differently from the mixing air, in this case, not the whole enthalpy of the extract air can be recovered. Assuming the efficiency of the heat exchanger being 60%, we can calculate by means of this formula the temperature T22, that is the temperature of the supply air soon after the exchanger and before the coil in this position. We get 29.2 Celsius. Since its absolute humidity does not change with respect to the absolute humidity of the outside air, we can calculate the enthalpy H22 of the air after the exchanger, that is 64.6 kJ per kilogram. And considering that the supply enthalpy is the same as for the mixing air, the cooling demand is negative 444 kilowatt, that is about 50% higher than the heat demand in case of mixing air. The psychrometric chart shows the transformation points. The air condition after the exchanger is P22. As we can see, its enthalpy is higher than the case of mixing air. Therefore, the cooling demand of the coil is higher. For the rotary exchanger, the heat and mass balance can be treated in the same way as for the plate exchanger. The only difference is that here the efficiency is higher. We neglect the mass transport across the stream, and we say that this exchanger can only transfer sensible heat. Assuming the efficiency of the heat exchanger 72%, we can calculate T22 with a similar formula used for the plate exchanger. We find 27.6 centigrade. And since the absolute humidity of the outside air still does not change, we find the enthalpy after the exchanger, that is 63 kJ per kilogram. The cooling demand in this case says negative 420 kilowatt, that is 5% less than the one calculated for the plate exchanger. For the closed loop exchanger, the heat and mass balance can be treated in the same way as per the other exchangers. The only difference is that the efficiency of the closed exchanger is lower. Assuming the efficiency of the heat exchanger being 53%, we can calculate always with the same formula the temperature T22 and therefore the enthalpy H22. That turns into 65.6 kJ per kilogram. And the cooling demand rises in this case up to negative 458 kilowatt. That is 3% more than the heat demand in case of the plate exchanger. As example for the thermodynamic recovery, we take a chilled water loop 712 degrees, also very standard. For refrigerant we consider R32 and we set the evaporation and condensing temperature according to the ambient conditions and process requirement as displayed. Consequently, we can determine the enthalpy values of the 4 stages of the cooling cycle. The EER calculation gives 3.69. Should we cool the condenser with the inside air in place of outside air, the condensing temperature is expected to drop of about 13 degrees. The new EER turns into 5.75. The cooling demand will be the product of the mass flow, also volumetric flow times density, and delta enthalpy. We land to negative 543 kilowatt. This value is very high because no recovery by exchanger. The power needed to generate that heat is the ratio between the cooling demand, above calculated, and the EER of the process. We get now 94.4 kilowatt. We want to compare this amount with the other 4 solutions where there is thermal recovery, but no thermodynamic recovery, and therefore EER stays as calculated upfront at 3.69. The resume says the least demand we have with the mixed air, 78.3 kilowatt, but the thermodynamic stays at the second place. That is not bad. All the others are much higher. Of course, any solution has advantages and disadvantages. We want to resume them in this table that I hope it is self-explanatory. For efficiency, the mixed air is the best, as we have seen, and for investment is relatively low, no exchangers. The investment for the thermodynamic is also low, since it does not need any additional equipment, just repiping. For the air quality, the best solution is when we have separation of the streams, also for plate, loop and thermodynamic. The loop exchanger, despite of the low efficiency, has the advantage to allow the recovery when supply and return streams are distant and can be easily retrofitted to existing systems. The thermodynamic is the least maintenance intensive since no exchangers and offers limited pressure losses. I hope, as always, that you have enjoyed my presentation. Please let me know your comments, your ideas for improvement. I appreciate it very much. See you next time. Bye bye.